Hello everyone, today we're going to look at usaco-training humble numbers. In this problem we're given a list of some primes from P1, P2, P3 to Pk. Okay, so then we're given a number n where we're supposed to find the nth humble number. So a humble number is defined as a number that is a product of a subset of the primes. So for example, 2 times 5, which would be equal to 10, so then 10 would be a valid humble number. So the nth humble number means the nth number from all the possible humble numbers, the nth one, sorted by their value. So for example, 2 would be the first humble number. And also the number 1 is not a humble number. So then 2 would be the first humble number, 3 would be the second, 5 would be the third, 6 would be the fourth, and so on. So in this example, 27 would be the 19th humble number from this set of numbers. Okay, so one approach would to be doing, one approach would to be doing generating all subsets. So this would take, So this would take 2 to the k to generate all subsets. And this would not pass because this would result in a worst case of 2 to the 100th, which is way too big. So then we cannot use this. Okay, so our next way is to basically generate each humble number accordingly. So for example, we can define hi as the ith humble number. Okay, and then we can just set h of 0 to 1. And we know that 1 is not a humble number, so we can just make it our 0th element. And then our hk, or actually it would be hn, would be equal to our answer. Okay, so now how do we calculate hi? For example, you see that originally, we have, for this example, we have a set of prime numbers as 2, 3, 5, and 7. So originally, you know that h of 0 would be equal to 1. So now we're going to calculate h of 1. What we're going to do is that we're going to loop through all the primes, and we're going to see for each prime which humble number can work for them. For example, you know that 2 can work with 1. So basically, these connections would be the possible pairs. So then you just multiply these two values together. For example, 2 times 1 would get you 2, and 3 times 1 would get you 3. And then you get the minimum possible of these values such that the product of these are greater than 1. So then you would get 2 for this example because you would take this way. So let's actually erase that. Okay, so let's just assume we know this is 2. So then again, when we're calculating h of 2, we're going to loop through another set of possible pairs. So we're going to loop through 1 of 3, 1 of 2, 1 of 5, and 1 of 7, 2 and 3, 2 and 5, 2 and 7. So then our optimal solution would to be taking 1 and 3. And this would take us a cost of 3, or basically a value of 3. Okay. And then after this, again, we're going to generate all the possible paths again. So we're going to have 1 and 5, 1 and 7, 2 and 3, 2 and 5, 2 and 7, 3 and 5, and 3 and 7. So then you notice that basically what you're going to do is that you're going to see that basically for 2, let's just say, if we want to make sure that 2 times a specific prime is greater than our humble of I, if we're going to look at humble in I plus 1, since humble of I plus 1 has to be greater than humble of I, then you know that basically 2 times, or basically this would actually be humble of J times P of I should be also greater or equal to this. And P of I minus 1 wouldn't work because if this is the condition, then this wouldn't be true. So then let's actually erase that and I'll show you. Okay. So let's just say we're calculating. So you know that our next value would be 5 here, 1 second. Okay, so this would be 5 and 7. Okay. So let's look at 3, or let's actually look at this. Let's look at this 2, for example. You know that when we're looking at 7, maybe our choice would to be pairing this with 3. Okay, so you know that this might be a valid combo. Actually, so I made a mistake here, so this should actually be 6, because that is actually our best answer here. So this should be our 6. So notice that this is the pair for 6. Now when you're actually looking for the next value, you realize that you don't actually have to try pairing one. You don't actually try, so you don't actually want to try to pair this or this, because if you have these in sorted order, then if you pair these, you know that these pairs would result in a lesser value than 6, which you don't want because you actually want them to be increasing. So then what we can do is that we can keep track of, let's call this last, so this would be last of I, so this would be the index of last prime. So for example, after calculating the 6, you're going to set the last of 2 to 0, 1, 2, 3, 4. So this would be equal to 4. And for 3, you see that this is going to be 0, 1, 2, so this would be 2. And you just set these accordingly. So then this can basically speed up the runtime a lot because we don't actually, or we actually eliminate some redundant information. So basically, that was kind of messy, but the pseudocode would actually look something like this. So we set humble of 0 to be equal to 1. Okay, so now basically for each humble, so for I in from 1 to k, actually 1 to n, because we're going to find all the humble numbers. We're going to loop through all the primes. So let's just say for j in, let's just say 0 to k minus 1, since we're using 0 indexing. So now we're going to try to use j actually. So then we have our last from before, and we know that we may always want to increment our last because our humble numbers are actually getting bigger and bigger. So then what we're going to do is that we know our last j would be equal to the prime. So then basically we want to increment our last while basically this value. So this would be humble of j times last of j. Well, this is less than humble, or actually you could say, well, this is less than humble of I minus 1, because you know that our next value, because you know that basically h of I must be greater than h of I minus 1. So then for this to work as a replacement, you know that you can't use this last. So for this example, you would just increment this. And after this, you know that h of I, since you want the minimum, would be equal to the min of h of I and h of j times last j. Okay. So this algorithm would actually run pretty fast, which would pass the constraints as well. Okay. So let's include bits. Okay, so we're given two numbers, n and k. So we have int n, or k and n actually in that order. Okay, so we're going to read in the k primes. So we can call this p. So we can read p of I. Okay, so now we're going to calculate our humble numbers. So again, we should have a list containing the information. So h of 1, 1, 2, 3, 4, 5. So you know that humble of 0 is equal to 1. So then we're going to calculate all the n humble numbers. Okay, so remember I said that we also have to keep track last, which is the index of the last prime that we may want to use. So then again, as I said before, we're going to loop through each prime. And then we're going to increment last of j while the product of these numbers are less than h of I minus 1. So while p of j, because this is the value of the prime, or actually, okay, so j is actually the value of the prime. So while p of j times h of last of j, so while this is less than or equal to actually, is equal to h of I minus 1, we're going to increment last of j. Okay, so after this, we know that this condition would meet the constraint. Or actually, there might be a corner case. So let's just say a number is really small, but that number times the largest prime is actually not able to be less than this, so this would actually go lower, out of bounds. So we could also add a case. So if last of j, it has to be less than k, because that's actually our, or it should be less than n. It actually should be less than I, because you shouldn't be using more than that as well. So then we just need to check if h of last of j, or actually should be p of j times, if this is greater than h of I minus 1, since you actually want to increase, you want an increasing humble numbers, then we're going to set h of I equal to min of h of I and this value here. So originally h of I would be equal to 0, so before here we're just going to set h of I to a pretty big number. Okay, so over here you're going to set, or actually going to print h of n, since you want the nth humble number. So let's actually run this. Okay. Compiling. Okay, so the primes are going to be integers. So yeah, okay, so I think we actually have to use longs here because the values can be quite big. So we're getting 27, which is correct for the sample case. But the numbers can be quite big, so as I said before, we're going to use longs. So instead of 1e9, we can use 1e18, which is a lot bigger. So let's submit this. Okay, so this is humble. Okay, so let's go here and select the file. Okay, so humble numbers. Okay, so I got it. Here we go. Okay, so that is right. If you have any questions, feel free to leave them in the comment section below. Bye.